Can you hear me?
Yes, ma'am.
Okay, thank you. Thanks. Okay, I think it is time to start. And what I would like to do is to start with a quiz that we had since Friday. And I wanted to show that the majority indeed identified the correct answers that you see here in green. However, we had only 37% accurate responses, which means that people identified, some of these people that identified the correct answers, they also identified the incorrect answers. And what I consider to be important in this particular case is to understand the fundamentals, because I have to tell you, without understanding the fundamentals, you will not be able to do a design. So what we are going to repeat all the time is that there are 3 particular attributes that we would like to design for. Number 1 is gain. Number 2 is noise. And number 3 is bandwidth. 3. Gain, noise, and bandwidth. There is, well, it could be 1 out of 100, maybe, amplifier designs that can give you all 3. I have not seen one yet, personally, in my whole career, which says that as engineers and looking at the probability, okay, of success, that an amplifier cannot give you all 3 at the same time. And that's why in design, we are talking about trade-offs. So in the material that we have seen so far in this course, there are some things that you need to keep in mind. So first of all, a conditionally stable amplifier cannot have both maximum gain and minimum noise, because each one of those is on its own an optimal. On its own is an optimal case, and they don't happen with the same conditions and operating or magic conditions. So we always trade off between the two. All right, so that we got it. But then we had 17 students who said that an unconditionally stable amplifier can have both maximum gain and minimum noise. That is not true. Being unconditionally stable or conditionally stable has nothing to do with maximum gain and minimum noise at this point. It only has to do with the ability of the amplifier to operate in a stable environment. All right. And number one in this stability will be, of course, two conditions. The bias of the amplifier is very important. And after that, if you set the bias, then of course the matching circuits on the front and on the end of the amplifier. But beyond that, the design of a stable amplifier faces the same issue between gain, noise, and bandwidth. They are competing, and you will see that in the examples we're going to solve this week. Okay. There are 6 individuals who said that the low noise amplifier is always unconditionally stable. I suggest that these individuals do go back and read carefully the material that we gave. There is no way. That's why we have unconditionally stable and conditionally stable amplifiers, because not all of them can be unconditionally stable. And 9 people said that a conditionally stable amplifier can never provide maximum gain. We do not know that. That is not a true statement, because there are conditionally stable amplifiers that can provide maximum gain, but obviously that can be at the cost of either noise or bandwidth. Okay, so I know these are complex concepts. I do appreciate that, but they are important. They are important because without having a good grasp of those, will be very difficult to do a design. Okay. Today, having said that, the exercise I'm giving you today, which I would like to do between now and Wednesday, is around similar topics. So please don't just in haste go and pick whatever answers. Read carefully, go back and look at your notes. This is the reason I'm giving you that. And respond to the exercise, which I have already opened and I have for today. And I have already seen people, okay, if you know all of this correctly, it's good with me, but don't rush into picking the wrong answers. Okay, so with that, I would like to ask for any questions, particularly specifically to this, and then I will move to examples we have to do to solve this week. Any questions? Okay, so what we are gonna do this week, knowing that the material we cover is not necessarily difficult. I mean, if you see, it's like recipes, all right? In fact, this is one of the few chapters in design of circuits that we are just following a recipe. It's after we do the things that the recipe tells us that we need to start thinking about how to trade off the designs. And we said that the design requirements. And then we said that we have 3 after stability. Okay, stability is 1. Stability is like, how can I say that? It's like you build a house, all right? Now there are many designs, many trade-offs when you buy a new house or you build a new house, you're gonna go in there. There are, of course, a number of trade-offs. How many rooms you're gonna have, where you're gonna place that, what kind of furniture you're gonna have, and all of this. And all of them are very important. However, none of them can be addressed without having a foundation that can hold your house, all right? So the same thing applies to amplifier design. The foundation for an amplifier design is stability. Stability is number one. It's like you place a foundation. You have not even designed anything yet, all right? By selecting the stable regions, it's like you place down the foundation for the house. Nothing else has happened. You don't have the rooms, you don't have the furniture, you don't have lights, you have no air conditioning, nothing. All right. And none of those can be discussed or even thought about unless you have a foundation to put it on. So this is exactly what happens, remember that, with amplifiers. Foundation for an amplifier is stability. After now, you identify the space in which, the space is not a point, is a whole space in which you have a stable amplifier. All right, you remember there are whole sections of the Smith chart. Then we are talking about the other three important requirements. Gain, which we spoke about, noise, and then bandwidth. We're going to leave the bandwidth for the end. We have talked about bandwidth a little bit on the surface, and we understand that bandwidth by itself, we said that bandwidth at a maximum gain is very narrow. All right. So immediately you heard that the maximum gain is something that happens at one point in frequency, and therefore your bandwidth is extremely narrow. All right. We talked a bit about this without designing anything specific for any specific bandwidth, I should say. Then we went gains and we saw the gain circles. We'll see them again. Now we're going to see them not alone, but together with noise. So I will introduce noise. Again, we have noise circles, all right? And from there, we'll continue with the design. So here is what you've known that this is now anymore what we know about our LNA. It's a transistor and has a input matching network here, and it has an output matching network. All right. So after we identified the stability of the amplifier, of course, it's a bias operating point, and then the frequency we are going to design it on. The whole thing now, the whole effort is to find the matching network at the front, this, okay, well, that is always a problem. This one, and the matching network at the back of the amplifier. That is the most critical thing. Since we've selected frequency for the amplifier and bias network, that means for this amplifier, we know all of S, all of the parameters, the scattering parameters, and some additional ones, as you're going to see in noise. Now, the formula number one, I will not ask you to derive it, but it's given to you. And that says that in a given amplifier, we have this. The noise of an amplifier is a function of the minimum noise, which comes out of the transistor. All right, all of these are generic: minimum noise, maximum gain. And now we see also Rn, which is called the noise resistance. And this one, the Y optimum. These are all parameters then a designer for the device, for the transistor, will give to you. All right, so there are people out there, not in this class, not us, who will give us a device. And you will see later that can be a CMOS, can be a BJT, can be everything, anything that you that may operate in your frequency range. And with that, they will give you different parameters that they have measured or they have calculated, and then they measure to confirm after the design, because the transistor needs to be biased, obviously, all right? There are circuits to make it biased. Otherwise, it does not mean anything. The designer of the active device is going to give you also its bias network. And in fact, more than one bias possibilities. So they will give you that. And therefore, you will have the S parameters for frequency ranges. You will have both magnitude and phase, the F parameters. You're going to have, in addition to that, when you design a device for noise, for a low noise amplifier, then the designer for the device is going to give you this. They will give you Rn, which is the noise resistance for the source. They will give you optimum Y. And now, how do we define the rest? YS practically is nothing else, but if you look at, let me erase this just so you don't get confused, because sometimes we use both G for admittance and we use like or C for admittance, and B also. People use different things, but this is the source admittance. So when we say Y optimum, that implies that the optimum source admittance for this amplifier to achieve a minimum noise is given by something, and they will give it to you. You're not going to have to compute that. That is given. Okay. Then the relationships are like here. For example, if you know YS, of course, is not going to be the optimum in any real design. It's going to be away from the optimum. But the YS then is given in terms of gamma S from here. This is a relationship that you have seen before, okay? Gamma S. Then for minimum noise, we said that this YS is nothing else but this optimal value, all right? So whatever YS gives you F minimum, we call that Y optimum. And then obviously, if you will see a gamma optimum is nothing else, but is another entity that is related to your Y optimum. So obviously your designer, the device designer, is going to give you Y optimum, and then you can calculate gamma optimum. All right. If we take all of this into consideration, then we can rewrite the above expression like this. All right, so now we have the noise of the noise figure of the amplifier is given by an expression that shows it's if your gamma S is equal to gamma optimum. You can see this here from the numerator. If this happens, then your F is only your F minimum. All right. But if that does not happen, because obviously you want to achieve some other things in your design, like gain, all right? You're not going to have an amplifier that has minimum noise but no gain. Why would you put it there? So if you do that, then your gamma S obviously is not going to be gamma optimum. And this term here adds a value to your F minimum. So now you can see how you start when with gain. When you want to achieve gain, you have to compromise your noise figure. Okay. In addition to noise figure F, we also introduce what we call a noise figure parameter. It's just something to help to simplify calculations. The noise figure parameter capital N is given by this, is a definition. And if then you you define n by equation 2, then practically your n can also be written like this one. Okay, so it's directly proportional to how far away you go from your minimum noise. All right, because of this, it is in the numerator of this, you have that difference between your real noise f and your minimum noise. Okay, now, what is it that we see? We see that all of these values of n, all right, so you remember we call that a noise figure parameter. So every n, every value of n from equation 2, every value of n corresponds to a value of gamma s. You see that? So since gamma optimum is given, it's a constant. There is nothing to do about it. But you can select your gamma n's. So what is interesting about noise? Noise only, if I go to the front, noise only impacts this part of your amplifier. So noise only will determine your gamma S and therefore your gamma in. How much is going to be your gamma in if I know my gamma S?
Complex conjugate.
Yeah. And so if I know my gamma S, if I select it, then I know my gamma in, and then you will see later from that I can find my gamma out, because gamma out here depends on gamma S, all right, as we will see. So noise only impacts the front of your amplifier, not the back, only the front, remember that. So then we go back to this, excuse me, not these ones yet, these ones, our expressions. As I said, so far, everything is given. We don't derive anything. Now, we identify that all of this n corresponds to gamma s, obviously. So all of these are the gamma s for every n, the gamma s is on the perimetry of a circle, all right? Where? What happens with these circles? C sub f is determined by gamma optimum and n. And again, remember from equation 3 here, n is a measure of how far away I'm going from f minimum. So for every value of n, I have a circle. And I know the center of the circle from here. And I know the radius. So the center of the circle before I go to the radius. The center of the circle is a number in polar form. It has a magnitude, which is the magnitude of gamma optimum divided by n plus 1, and has a phase, which is the phase of gamma optimum. Okay?
Dr. Katehi?
Yes.
How to draw that on a...
Okay, I'm getting there.
Cards.
Then RF, again, is a constant, is a real number, all right? So the noise circles will help you define gamma S, I'm telling you that. Then from this gamma S, we can define gamma out, and from gamma L, that is equal to the complex conjugate of gamma out, then we can define gamma L, all right? So what I decided to do as an example is I will start with the gain circles, because I would like to do a review, which is nothing different in terms of the same circles. You put them there, but they correspond to gain, and then I will go to noise, all right? But I would like to remind you the gain circles first, and then we'll go to noise. So this is where we were last time. So in this particular case, you did that, we did this very fast last time. I will do it, I will go through it, and then we'll continue with noise. So, and then we have another example, which we'll probably finish next on Wednesday. So we have a BJT here, and this BJT is given by all of this. You see, so you have your scattering parameters, you have in the BJT, you have your bias, VCE and IC, bias circuit conditions, you have your operating frequency, 4 gigahertz, and the maker of this device has given you for 4 gigahertz these scattering parameters, and in addition, the maker of the device has given you the F minimum. This is the minimum noise this device can have. You cannot go below 2.5 dBs, okay, for a 4 gigahertz. It has the gamma optimum given to you and has the noise resistance, which is 3.5 ohms in that frequency and on those conditions. Okay, now we start, remember, we start with what we have already seen in the past, and we'll do it for review. All right, every time we have to review that so we don't forget about it. So this one is, you never design an amplifier for one thing. All right, so whenever you design an amplifier, you have to put at least your gain and your noise there. The bandwidth is another thing, it's a level higher in complication, but at least gain and noise have to be there. So we start with the gain here. What we've seen is, if you remember from the previous, when we have a low noise amplifier, which are 3 2 ports connected, then how much is the total gain of this? Remember what we said? How much is the total transconductance gain of this? Who is going to tell me?
Product of each gain?
Yes. Yes?
It's multiplication.
Yes, it's the gain of each, the product of the gains of each state. Exactly. So it's G sub S, which is the gain of the S of the input matching network, G naught, which is the gain of the low transistor, and G L, which is the gain of the output. All right. How much is G naught? We said that G naught is S21 magnitude square, always. So then the maximum gain for GT will be controlled, all right, by the gains of the matching of the green 2-port stage of the input stage and the output matching stage, GS and GM. And those are given, these maximum values will be given to us by practically well, for any frequency, these are true not for the maximum, these are true for anything really. So your GS is going to be that as a function of gamma sub S magnitude, of course, and gamma sub in. And what happens if gamma sub in is the complex conjugate of gamma sub S? That's going to give eventually the maximum value of G's, okay? And then G sub L is also a function of gamma sub L and S22 in this particular case. So for maximum available gain, to remind you also, all right? All of this is as a review to remind you. If we needed maximum available gain, which means that we could have a horrible noise, but we will have a lot of gain, all right? But the noise can be unacceptable. It doesn't matter. If your maximum gain is what you're looking for, regardless of anything else, we have already looked at the formulas for this. These are the ones. You don't need anything else. But unfortunately, that is not always acceptable, or most of the time it's not. Okay, because we need other things like noise, low noise. Now, therefore, we have, however, a value for the GT max, just so we know how low we can go from that. All right, so a lot of times you want to know what is the maximum to see how much you compromise. Because, okay, you may want to compromise your maximum, but you may not want to go from 14.7 dBs to 2. That's way too much compromise. A lot of times when you do a compromise between noise and gain, you don't maximize one and then you destroy the other one, all right? You always try is like somewhere in the middle. So we want to know how far we are from that. Okay. And then we also have from previous, these are the gamma in terms of gamma L. You see now that in gamma in, your gamma L comes into the picture, all right? Always your gamma in is gonna see what is happening at the other end of the amplifier because you're looking through the amplifier towards the load. And gamma out is a function of gamma S because you're looking through the amplifier towards the source. Okay, that's what we said before. Remember, now I want to remind you. Remember what I said, that the moment you define this, the moment you define gamma sub S, then I have really defined this one. But of course, I would like to make eventually gamma out to be complex conjugate of my gamma L. So practically, if I define my gamma sub S, and then I define my gamma sub out, then I have defined practically my gamma sub L for a maximum gain under those conditions. If I find my gamma sub L, if I define my gamma sub S, excuse me, if I define my gamma sub S for maximum gain in the input front, then I will always define my gamma sub L for maximum gain at the output front, and then I will have maximum gain throughout. But if I have noise considerations, I will not define my gamma sub L for maximum, excuse me, my gamma sub S for maximum gain at the front. I may define it for gain and appropriate noise. And then, however, I will always define my gamma out like this. So practically, it's gamma S that is changed by the noise considerations, but always at the end, at the output front, we have a conjugate matching. All right, so what that means. If I go, again, summarize now. If I go for maximum gain, regardless of anything else, then it's maximum matching, is a conjugate matching at the input, conjugate matching at the output. Is that clear? We've seen that, okay? However, if I wanna have gain, but at the same time I want to achieve low noise, then I compromise my gamma sub S, but I always keep my gamma sub L to conjugate, complex conjugate relationship, so conjugate matching. So it's only my gamma sub S that is compromised, but my gamma sub L always complex conjugate matching, okay? Any questions about this? All right. Now, interestingly enough, it shows here that by, and that's where this discussion is going to stop until you bring the noise circles, which we're going to do right now. And I will do it in real time so you can see it, because sometimes when I have it already done, then it may be difficult for you to see the steps that I'm taking. So the last thing here that shows to you is that if I put here gamma sub S to be gamma optimum, all right? So I don't make gamma sub S complex conjugate of gamma in, no. But I choose gamma sub S to be my gamma optimum. And what is that gonna do? It's gonna give me what? The minimum noise. If I do that, then immediately from these relationships that I gave you, you will see that my G sub T goes from 14 point something dBs to 11. Now, do you remember how much of a change of 3 dBs is in an magnitude, not in dBs, but in real magnitude. How much is 3 dB change?
2 times.
Half, rather. Okay, so when we go from 14, which is true, when we go from 14 dBs to 11, you may say, well, okay, you know, I'm still good. Yes, your gain has gone down by 50%. Your gain is half right now. That's what 3 dBs mean. So now you can see why I may not be able to go to gamma optimum here later. All right, because maybe going from 14 dBs to 11 dBs is too much if it's half of my gain. Anyway, so that's what you at that point, therefore, now that you know what kind of space you are in and what is happening, when you go to optimum gamma, which means minimum noise, you know where you're going to be with minimum noise. 3 dBs down, like half of your gain. So if you have an application where you don't need, you cannot afford this much reduction of your gain, and you have to start thinking about the noise, now you have to go and introduce the noise. Okay, now it's clean. Let's go at this point and look at the noise circles, because that's what I need. And you remember the recipe. So here, now, where are my noise circles? Here, I'm gonna take this so I remember it. All right, I'm gonna take this and copy it down, so I would not want to go back and forth, copy it, and then come here, and I will put it here so I can see it. Okay, now the, gamma optimum. Also, I'm gonna remember how gamma optimum is, and it has been given to us in the problem, as a matter of fact. So where it is here, gamma optimum is this. I'm gonna copy it also. Copy. And I will put it here so you remember it. And then I have n. So for this now, you see that I don't need anymore to write the circles. Eventually, I would like to know what kind of f n gives me, all right? Because n by itself is a constant. But here is what I have, gamma optimum. So I want to find all of the circles that have centers C sub f. So since C sub f is a complex number on the Smith chart, it has a magnitude. So C sub f magnitude here is going to be magnitude of gamma optimum divided by n plus 1. So when n equals 0, C sub f magnitude is just gamma optimum. And when n is different than 0, the angle, the phase of C sub f is always the phase of gamma optimum, which is 166 degrees. So practically, by drawing the line that goes through 166 and then 166 degrees, if you remember, I read those from here. All right, if I go around, 166 is here, is in this space. And 166 is 246 is here somewhere. So I will draw a line that connects the center of the Smith chart. I will draw enough for now, there. And then I will move it to the right place. And it's gonna be 62, 64, I think. Somewhere here, isn't it? Yeah. No, it's 60. 462, 64, 66, 166. So what happens with this one is that all of my circles are on this line. Okay, all of the noise circles, C sub F, are on this line. Now, what I would like to do is to also point to the C sub, the point C sub F that gives me gamma optimum. That particular point is going to give me a minimum noise. All right, it's only one point for minimum noise. There's not a circle, because if you remember from this expression here, if I select n equals 0, which gives me C sub F to be gamma optimum, therefore I have a minimum noise, R sub F is 0. Okay, because n equals 0, and it's going to give me, so it's 1 point, your minimum noise. All right, let's now find it. So I'm going down here, and the magnitude of gamma optimum is 0.475. So I'm going down to this linear scale. Sorry, this linear scale is here. I'm finding 0.45 something, and then I'm gonna write here, and then I will center it. I'm gonna write this line. There. Maybe it's not quite there. And let me see, is 0.475. Okay, so 0.475, if I go here, this is 0.6, 0.8, somewhere here. All right, and then I extend this line. Let me see. Until I find this intersection up here. And then I draw a circle that goes through that plane. Okay. So I will draw this one. All right, so that's somewhere here. Okay, approximately some there. And this is a constant VSWR circle, if you remember. And then the intersection between the blue line and the circle gives me C sub F. So my C sub F here, optimum, is this one. So that is the point, gamma optimum. Okay, if you wanted to design an amplifier for minimum noise, but no consideration for the gain, then you have to pick this point as your gamma S. So for minimum noise, your gamma S will be gamma optimum, and that will give you in your design N or F to be F minimum. Okay. Now, obviously, when N changes, both the location on this blue line of the center and the radius change. All right, the radius for the optimum is 0, so it's 1 point. We talked about that. Okay, now let's try to go to a different value of N. What time is it? I have a few more minutes. So a different value of N. If you go, you cannot go to N to be too large, I have to tell you, because if N becomes too large, then your noise figure becomes too high. So for example, if I were to go and look at the noise figure here, let me see it on the side. Here. Let's look at this one. And I will take it, this one with us down there in the design, copy here, and then go down. So let's put even this one here. All right. Look at this. It has n is directly related to the difference between the two. The 4 Arsa band over Z naught is constant, and the 1 plus gamma optimum is a constant. So you have a direct change in the values between F and F sub min. And if you plug in values there, you're going to see that your N value cannot change this much. So for example, I could make N to be like 0.1, 0.14, 0.2. So in fact, I can choose, if I were to put this one up here, I can choose an N which is 0.2 and see what happens. If I choose an N which is 0.2, then my C sub F becomes optimum. So the value of 0.475 divided by 1.2. And the value of 0.475 divided by 1.2, 0.475 divided by 1.2 becomes 0.395. And 0.395 here, it's a different line. I will use the green one to see. And it's right here. All right. And if I draw this line right there, so, and then I draw the circle, practically, I will, let me draw the circle to see. I will erase this one so you remember now that at that point the gamma optimum is F minimum. Okay, now I'm drawing this circle here. Did not take it, it was too bad. No, did not take that either. Okay, this one, approximately you need to always fix it because the circles are concentric. Okay, so if you move it a little bit, somewhere here. So the point, the green point, the new C sub n does not matter for now. The new C sub n is right here somewhere. All right. Now I don't need the green circle. I will remove it just so we simplify things. Or you want me to leave it? That's okay. I leave it just so you remember how we got that point too. Usually I would remove it myself. So this is this. Now let's find the R sub n. Okay, we need to find the radius. R sub n here, or R sub f rather, the way I have it. R sub f is square root of 0.2, 1.2 minus that 0.475 square, and that is divided by 1.2. So in fact, what is this going to give us? How much of a radius is going to give us? It's going to be 0.475 negative plus 1.2 times 0.2 and square root of that divided by 1.2 is going to give 0.367. The radius of this is 0.367. So we'll go here, 0.367 along from this point to this point somewhere. So it's this distance. So I need to draw a circle with this distance somewhere from the new. So if I do it approximately now, it's going to be a circle, a different circle. I'll give it a different color, this blue one. And it's going to look like, let me see, like this. Okay. Maybe a little smaller. You have to be accurate when you do that. Obviously, now I'm trying to show you. Okay, this circle corresponds to n, why n? N let's see how much n equals 0.2. This is the center, all right? There, let's see what kind of f it gives, because gamma optimum gives us our f minimum. And now we want to see, in fact, the f minimum, it was given to us. Let me see. F minimum 2.5 dBs. Now let's see how much is going to be this new f from this expression here. So, and if we find f from here, practically, f is going to be f minimum plus 4r sub n divided by z naught times 1 plus, okay, this one, let's do this. Okay, put it here so we can see it. All right. F minimum gives is f plus f equals f plus f minimum equals f minimum plus 4rn divided by z naught, and that divided by that. Okay. 4r sub n divided by z naught. R sub n, if I remember, was like 3.5 ohms. So practically that will be f minimum plus 4 times 3.5 divided by 50, and here it would be 1 plus 0.475, and that was 72, I believe, or something. So now this new addition, all right, is what is going to change your F minimum, and we will do this next time. I suggest that you calculate this value for this F here. Because that here is going to show you how your F changes the moment you change your N a little bit, all right? And then what we are going to do next time is we're going to add on the same Smith chart the gain circles. And then you're going to see how your gain circles will be somewhere else, all right? They're not going to be, they're going to be intersections. So you will see that maybe your maximum gain cannot be achieved with optimum, not maybe. You will see that your maximum gain, which is going to be someplace else on the Smith chart, is going to be far away from your gamma optimum. That's when you see you cannot do both. And then we are going to start doing the same circles, all right, around the maximum gain next time to see how they intersect and what it means, how do you then start thinking about what point to select. So what we've done today, to remind you, we reviewed the maximum gain and the circles for the gain, even if we have not put them here. We put down the expressions for the noise circles. We drew a couple of noise circles. I would like you then maybe to finish this one and then do one more value. And then we are going to add the gain circles. I will come next time. That is going to be ready for you to see. I'm not going to do it in real time, but I did it now because some of you still have questions on how to measure and how to find a gamma on the Smith chart. Any questions? I heard somebody with a question. Is there a question?
Yes, I have a question.
Yes. Go ahead.
The green circle is going to give me the F minimum when it's n equals 0.2. Is that correct?
No. Oh, the green circle. Yeah, sorry. You said it's going to give you what?
F minimum?
No. F minimum is at the gamma optimum. You see the pink dot?
Yes.
There is no circle that goes to F minimum. It's only one point.
Okay.
And it's this one. Only this one. Circles, then you start having circles when you move away from it.
I see.
All right, because when your N is 0, to get your minimum, all right, your F becomes equals to F min if your N equals to 0.
Okay.
And to be able then to have with N equals 0, your R sub F becomes 0. You see it here?
Yes.
Yeah. So it's only 1 point for minimum noise. You start having circles after you go away from the minimum noise. Any other questions? Okay. Please review this material. And I have another, what I found, which is interesting, because now next time, you're going to see a real example that, in fact, in 2007, I found a paper. You'd see now how with this one, we start designing real amplifiers. You know, it's not just an academic exercise, as many people say. These are real amplifiers. So the next example after we finish this one is going to be on an amplifier that was a low noise amplifier, which was designed at 60 gigahertz. And that was in 2007. And in 2007, that was in fact something that people published to see how things have changed since then. All right, there is tremendous change in technology. The last thing I wanted to say, maybe I'll leave time to do it next time when we meet. I wanted to make some comments because I graded all of the critiques, and I think a lot of people did great work. Some people did minimal. That's okay. I mean, it's a distribution always. But I wanted to make some comments about some of the on the style on how we do a critique. Rather, I will do it next time. And I was thinking that in the following weeks, I will give you as a homework one solution that I have done which is wrong. And then I will ask you to find the errors and then critique my work. Maybe it's going to be easier to do it on somebody else's work. But I will do it next week sometime. All right, that's with that. We'll talk to you on Wednesday. And we have office hours in about half an hour.
What kind of critics do you expect?
What kind of critique I expect?
Academic or like mechanical? If such kind of mechanical or only like an administrative critic, I want to say something. Excuse me? Can you hear me?
Okay, to continue here, because I don't know whether the other one has a timer or something in the Zoom, but I think the moment we go over an hour and a half, it starts buzzing. Can you hear me now?
Yeah.
Can you hear me?
Yes.
Can you hear me now?
Yes.
There was
Hello.
a question I believe somebody asked, but I will respond to it next time since many students have already signed off. Have office hours in about half an hour. Thank you.
Thank you, Prof.